Let me see here. Can everybody see my screen, but cannot
Yes.
see the file? Okay. Can you see my file though? Okay. Can you see my file now only? I don't have access to the chat since I'm sharing. Okay. So again, don't have access to the chat, or if anybody has a question, please unmute yourself. I cannot see any of you guys, okay? So again, today we are doing a final review for Math 13-14. So let's go ahead and get started, okay? So let's start with linear equations and finding intercepts. So in this first example, find any intercepts and test for symmetry with respect to both axis and the origin. Okay, so we have this equation y is equal to minus 2x plus 1. So it's nice, it has it already in our slope-intercept form. So for us to find the intercepts, we need to set one of them equal to 0. So if we start to find our x-intercept, well, we'll set y equal to 0. Okay, so let's go ahead and do that first. If I set x for my to find my intercept, I'll set or to find my x-intercept, sorry, I'm going to set y equals to 0. So then we have 0 is equal to minus 2x plus 1, and we're going to go ahead and solve for x. So we'll subtract 1 on both sides, divide by a negative 2 on both sides, and we get that x is equal to 1/2. Okay. So our point here is x is equals 1/2 when y was equal to 0. Now, to find our y-intercept, we'll do the opposite. We'll set x equal to 0 and solve for y. Okay, so we'll do this. Everywhere we see x, we'll put our 0. So negative 2 times 0, that's 0, and 0 plus 1 is 1. So our y value is 1. So our y-intercept when x is equal to 0, y is equal to 1. Okay, so now we want to do is we want to check for symmetry. And the way we do that, first we have this graph, right? We have a line, but we have some rules to check for symmetry if we didn't have a graph. So for us to check if it has x-axis symmetry, if we would change the sign of the y, and it would still give us the same equation, then it has x-axis symmetry. So let's go ahead and check for x-axis symmetry. So the way we would do this is, again, we would change the y value. We replace the y with a negative y, and we would solve for y. Okay. So when we do this, if we replace the y with a negative y, and we solve for y, we would see that we would have an equation 2x minus 1, which is not the original. It's not equal to what we started with. So it has no x-axis symmetry. Okay. So for us to see if it has y-axis symmetry, we replace now the x with a negative x, and then we solve for y again. So in our case here, when we replace x with a negative x, we get again y is equal to positive 2x plus 1. It's not the original equation, so it has no y-axis symmetry. And then finally, to check for origin symmetry, we'll replace the sign for both negative x and negative y, and we would solve again for y. And if we do this, again, we end up with a different equation. We get y is equal to minus 2x minus 1. So it's not the original equation. So this linear equation has neither x-axis symmetry, y-axis symmetry, or origin symmetry. Okay. So now let's look at an example dealing with a circle. So it says, write the standard form of equation of the circle with a given characteristic. So the characteristics that they're giving us here is a center at negative 4, 2, and a radius of 2. So let's recall the equation for the standard form of a circle. And the equation is x minus h squared plus y minus k squared is equal to r squared, where our center is at negative 4, 2. Our radius would be 2 here. So all we have to do is go ahead and place in what we have, what we know. So again, we place a value for h is negative 4, a value for k is a positive 2, and r is 2. Now we have to do is just simplify. The x and with a negative or minus a negative 4 will give us x plus 4. Here we go. And then the y minus 2, we don't have to do anything with that one. And then 2 squared is 4. So we have our answer. So this would be our answer. X plus 4 squared plus y minus 2 squared is equal to 4. Okay. All right. Let's look at a different example now. It says here, write equations of the lines through the given points, parallel and perpendicular to the given line. So what we know about parallel lines and perpendicular lines. So parallel lines, for two lines to be parallel, they have to have the same slope, different y-intercepts, okay? And for perpendicular lines, I like to say that it has a opposite slopes, right? So let me give you an examples of this problem. So if you see that the most important for us to find out if a line is parallel or perpendicular, we need to know its slope. So the equation here that they're giving us, they gave it to us in general form, so it doesn't tell us much. So the first step that I would do is convert this equation into slope-intercept form so I can see what the slope is, okay? So when I do this, I'll convert 8x minus 2y is equal to 3. And I convert this into slope-intercept form just by solving for y. And when I do this, I get this equation. Y is equal to negative 3 halves plus 4x. So what this is telling me that my slope is, that my slope is 4. Okay, I'm not interested in the y-intercept. The y-intercept here is negative 3 halves, but what I am interested is the slope. So now that I have a slope, I can come up with an equation that's parallel to this given equation. But they give us another piece of information. They want our line to go through this point. It has to go through the point 8, 1. So for me, the best way to do this is using my point slope formula. Okay. So my point slope formula is this: y minus y1 is equal to m times x minus 1. Again, where my m is my slope and the x1 and the y1 is the point that I want my line to go through. So then now that I have everything, again, my point is 8, 1. This refers to the x1 and the y1. My slope is 4. Let's go ahead and plug in and solve. So when I do this, I have y minus 1 is equal to 4 times x minus 8. So now all I have to do is distribute the 4 and simplify and solve for y. Okay. So when I do this, I have 4x minus 32 when I distribute the 4. Now what I'm going to do is I'm going to move the negative 1 to the other side by adding 1 on both sides. So it's on there. Okay. So I have y is equal to 4x minus 32 plus 1. So simplify, we have y is equal to 4x minus 31. So this line is parallel to my given line because they have the same slope. And as again, if you recall, our original line had a y-intercept of negative 3 halves, I believe, and this one has a y-intercept of negative 31. Same slope, different y-intercepts. That means that they are parallel. All right, now let's look at the perpendicular. So for perpendicular, what we have to do is take the reciprocal of the slope. So if I were to convert the slope into a fraction, this would be 4 over 1. So the reciprocal of 4 over 1 would be 1 over 4. But on top of that, what I have to do is I have to change the sign because, again, parallel and perpendicular are opposites of each other. So if my parallel was a positive slope, my perpendicular has to be the opposite side, has to be a negative, right? So then we have our perpendicular slope would be a negative 1/4. So I would do the same process that I did before. I'm going to use my point slope formula because I have my point at the the equation needs to go through, or the line needs to go through, and I have my slope. In this case, it's the negative 1/4. So let me go ahead and substitute what I know. So again, I know my point, and I know my slope. So y minus 1 is equal to a negative 1/4 x minus 8. So the first thing I need to do is I need to distribute this negative 1/4 into the parentheses and simplify. Okay? So when I do this, negative 1/4 times x and a negative 1/4 times a negative 8. Okay, so let's go ahead and simplify. So here, let's do it. Let's go one more time. My negative 1/4 x stays the same, but a negative with a negative is going to be a positive, and 8 divided by 4 is 2. So that's where I get this 2 from. Okay. Then my last step is to add 1 on both sides to get my equation. So this is going to give me y is equal to negative 1/4 x plus 2 plus 1. And when I simplify, 2 plus 1 is 3. So I have now my equation that is perpendicular to the given equation, because again, what made it perpendicular was my opposite slope, this negative 1/4. Okay. All right. Let's look at basic operations of functions. Okay. So if we have these two functions, f of x is equal to 9x plus 1, and g of x is equal to x squared minus 1, let's go ahead and add these two functions together. And the syntax that you see for a here is this: f plus g of x. What this means is just adding f of x with g of x. So the way I like to do this is just, I like to write it down this format. I like to write that f of x plus g of x. And by me writing this, I just substitute and solve. So f of x is the one in red, the 9x plus 1. The g of x is the one in blue, which is just x squared minus 4. And I'm going to simplify by combining like terms if I can, right? So I have only one x squared term, so that stays the same. I only have one x term to the first power, so that stays the same. But I have two constants that I can combine. These are my like terms. So I have a plus 1 with a minus 4. That's going to give me a minus 3. So the addition of function f with function g is x squared plus 9x minus 3. All right, now let's subtract functions. I would do the same process. This is a syntax for subtracting functions, f minus g of x, but I like to rewrite it in this format. All I'm doing is subtracting f of x with g of x. So now all I have to do is substitute. F of x is 9x plus 1 minus, I have to be careful because I'm subtracting and I have 2 to my function. I have to put this in a parentheses, okay? So we have x squared minus 4. So before I can do the subtraction, I need to distribute that negative sign to both of my terms inside the parentheses. So a negative times a positive x squared is going to give me a negative x squared. A negative times a negative 4 is going to give me a positive 4. And then I'm going to combine my like terms again. I only have one x squared term, which is a negative x squared, so I leave that alone. I have a lonely linear term, x to the first power, the 9x, so it's plus 9x. But I have two like terms, which are my constants. I have a plus 1 and a plus 4. So 1 plus 4 is my 5. So the subtraction of function f with g is negative x squared plus 9x plus 5. Okay, let's do c now. What this syntax says is fg. This means when we have two things next to each other without a symbol, that means multiplication. I'm going to multiply function f with function g. But I like to rewrite it with what I'm doing. This means that I'm just going to multiply function f with function g, and then I just substitute. Function f of x is the 9x plus 1. Function g of x is x squared minus 4. So to simplify this, I'm going to do FOIL. The 9x has to be multiplied with both of the two terms of the other function, and the plus 1 has to be multiplied with the other two terms of the other function. So 9x times x squared is a 9x cubed. 9x times a minus 4 is a minus 36x. Now the 1. 1 times x squared is just the x squared, and the 1 times the negative 4 is just the negative 4. And if I can combine like terms, I would, but I can't. All of these are all different terms. So if you were to put this inside, again, in your homework, when you put it in the computer would not have any objections with this answer. But us that in the math world, we like to have things standard form. So standard form for us is our leading coefficient or the degree is always the highest exponent, and then all of the others are in descending order. Again, you don't have to do this, but it looks nice. So I would like to write the answer as 9x cubed plus x squared minus 36x minus 4. Okay, and let's do the last one, D. Let's divide function f with function g, and the syntax that you'll see is like this: f slash g, or f divided by g of x. Again, I like to rewrite it. I like to rewrite it to what they're asking me to do. They want me to divide function f with function g. So function f of x is just 9x plus 1. Function g of x is just x squared minus 4. It says none of these, I can't simplify any of these. I can't factor out anything. Nothing cancels because these are all a part of each other. Um, the answer just stays like that. The answer is just 9x plus 1 over x squared minus 4. Okay. All right. So let's so one of the things that you might be asked again on your final, because you were asked on your homework, is that they'll ask us, what is the domain of our answer of f divided by g of x? So again, and the reason why they're asking us on this one is because since we have a fraction, we never want the denominator ever to be equal to 0, right? So since we have a denominator here of x squared minus 4, we need to find out, will this function ever give us a value of 0? And if it does, then it creates a restriction on our domain. We have values that we cannot use for x because we'll get errors or undefined. So let's see, what is the domain of this function? So to do that, what I'm going to do is I'm going to set the denominator, which is x squared minus 4, equal to 0. So here, I can just solve by adding 4 on both sides, which will give me x squared is equal to 4. Take the square root of both sides, and I see that x is equal to plus or minus 2. So that means if I would use a positive 2 or negative 2 for this function, I would get an error on my calculator. It would be undefined because the denominator would become 0. So then in interval notation, the domain for this function is from negative infinity to negative 2, union from negative 2 to 2, union from 2 to infinity, because I cannot use a negative 2 and the positive 2. Okay, and we all should be familiar with this. Okay, but that's what we're doing. We're reviewing all our knowledge that we did this semester. Okay, now let's look at inverse functions. Okay, so you had done a test to find out when you were given a graph, to find out if a graph was a function. If you all recall, you would do the horizontal line test, right? That if this imaginary horizontal line only crossed my graph once, then the graph was a function. Well, if we want to find out if a function has an inverse, well, opposite to a horizontal line would be a vertical line. So that's how we would test a graph to see if it has an inverse. What we would do is we would perform a vertical line test. And if our imaginary vertical line only crossed our graph once, then it meant that it did have an inverse. So if I would do that to the graph that is given here, if I would do an imaginary vertical line, I would see the imaginary vertical line would cross my graph only once. So then that means that this graph has an inverse. Okay. So again, this is what I just said. A horizontal line test is to check to see if it has a function. So to find if the function has an inverse, we would do a vertical line test. Okay. All right. So let's look at this example. Determine whether the function has an inverse. Now on this one here, since we don't have the graph, what we want to do is we want to find if it has an inverse. All right, so first what we need to say to ourselves, what type of function is this? So this function here is a root function, right? So it will pass my vertical and a horizontal line test, right? So let's see, do I have a graph of it? No, I don't have a graph of it. But if you will recall, this graph got shifted 8 units to the right, and it's like a half of a parabola, right? So it does pass my vertical and horizontal line test. But what if they asked us to determine what that inverse was? So to do that, the first thing that we would need to do is replace f of x with what it was used to be before. And this used to be an equation, which was y equals, right? So that's the first thing that we would do. We would replace the f of x with the y, giving us an equation. Y is equal to the square root of x minus 8. Then the next thing that I would do is I would swap. I would interchange the x and y values because that's what I want. I want the opposite, right? So I would replace my x and y values, and I'm going to end up with this. X is equal to the square root of y minus 8. So then to find my inverse, I'm going to solve for y. So the first thing that I'm going to do, I'm going to square both sides. So I have x squared is equal to the square of y minus 8. So we know that when we take the square root of a square, we get an exponent of 1. I know that some of you like to say that it cancels, but it really just becomes of an exponent of 1, which gives us x squared is equal to y minus 8. Then I'm going to add 8 on both sides. Now I have my equation. Y is equal to x squared plus 8. So to indicate that I've just found the inverse, I'm going to replace y with this notation, f to the exponent of negative 1. So this means inverse. F to the negative 1 of x means that x squared plus 8 is the inverse function. Okay. All right. Now let's look at another example here. It says, sketch the graph of the function by applying the leading coefficient test, finding the real zeros of the polynomial, plotting sufficient solution points, and drawing a continuous curve through the points. Give me 1 second. Okay, there we go. So what they want us to do is, the end result is they want us to graph, right? So first, apply the leading coefficient test. So here we have several options, but let's go ahead and review our leading coefficient test. Let's see, do I have it here? Yes. So what is our leading coefficient test? So our leading coefficient has to deal with the degree of the polynomial, whether it's even or odd. So um, an even function is a function that has an even exponent number. An odd function is a function that has an odd number exponent for the degree, yes? And when we know the highest exponent number refers to our degree of our polynomial. Now, the coefficient related to this highest exponent is called our leading coefficient. Now, if that number is a positive value, if you see this first graph here, if I have an even function and my leading coefficient is a positive value, my graph will rise on the left and on the right, okay? If I have an even function and my leading coefficient is a negative number, then what that means is my graph is going to fall on the right and fall on the left. Now, if we have an odd function, okay, and we're just using the cube as an example, but an odd function again is any exponent or degree of an exponent that it's an odd number, okay? So if our leading coefficient is a positive number for an odd function, it's going to rise on the right and fall on the left, okay? If we have an odd function and our leading coefficient is a negative number, it's gonna rise on the left and fall on the right. So if we look at our example here, we see that we have our highest exponent is a 2. So that means that a 2 is an even number. So this means that our function is an even function. Now, if we look at the coefficient of this degree, we have a negative symbol. We have a negative 1. We don't write the 1 here, but we know that there's a 1 here. So it's a negative 1. So then that means that this graph, based on our definition, is going to, the graph of the function is going to fall to the left and fall on the right. Yes, it's this, the second one right here. Okay. All right. Oh, here we go. So we circled it. So this, the answer for this would be the C part. The graph of the function falls left and falls on the right. Okay. Now it says B. Let's find real zeros of the polynomial. So here we have a quadratic, right? So to find the real zeros of the polynomial, we can do several things, right? We can factor it, we can use our quadratic equation. So let's see here. What option do we do? So again, all these methods were from chapter 2 to solve for our real zeros. So in this case, what we did was factor it, which is great. This is my first choice. Now again, for those of you when you get problems like this on your final, the best way to solve these right away is try to factor it. But if you can't factor it within the first 2 minutes, or you can't see it, then don't waste the time, because it might not be factorable. So then the one that you will never go wrong with is your quadratic equation. Your quadratic equation will always give you the real zeros. Okay, so in this particular problem, we got lucky. It's factorable. So minus x squared plus 12x minus 32 factors in this fashion, x minus 8 times x minus 4. So I know that the product of two numbers, for it to be equal to 0, that means either of these two numbers or both of them are equal to 0. So let's find out what values of x will make this product 0. So if you don't see them, set them equal to each other. X minus 8 is equal to 0, or x minus 4 is equal to 0. Here, we can see that if x is 8, we would get a 0. And in this one, if x was 4, we would get a 0. So the zeros for this problem are at 4 and 8. Okay. So now that we have zeros, what we can do is we can find additional points to help us do a better graph. And one of those is finding our y-intercept, right? So to find our y-intercept, we set x equal to 0, and we find out that our y-intercept is at y is equal to negative 32. Since we know that we're dealing with a parabola, we can use our formula to find the vertex of the parabola. And the formula for this is to find our x value of the vertex, we do a negative b over 2a. And then we put that value into the function that give us our y value. Now also, just to recall, this the format of a quadratic is in the form ax squared plus bx plus c. So in my problem here, my a is a negative 1, my b is a 12, and my c is a negative 32. Okay, so knowing these values, I'm going to plug them in. B is a 12. My a is a negative 1. So when I simplify this, I get a positive 6. Yes? So to get my y value, I just plug it into the function. Negative 6 squared plus 12 times 6 minus 32. This will give me 4. So my vertex is at 6, 4. So again, I have zeros where the graph crosses the x-axis. I know the behavior of the graph. I know that it's going to fall to the right and fall on the left. I know the y-intercept where it's crossing the y-axis, and I know its vertex. So with all of that, I put all this together. Okay, so here's my vertex at 6, 4. It crosses the x-axis at 8. Now, it crosses our y-axis at negative 32, so we can't see that, but we know that's going down because our behavior, again, of the graph is pointing to the left down and to the right down. Okay. All right. Let's go to another example. This problem says, find the rational zeros of the polynomial function. So we have f of x is equal to x cubed plus x squared minus 9x minus 1. So the first thing for us to find the rational zeros, for us not to just pick numbers at random and go through a lot of numbers to try to find a zero, what we can do is use our rational zero test. And our rational zero test Again, it's just a test to minimize our possible options for finding a zero. Okay, so the rational zero test require us to know the factors of the constant and the factors of the leading coefficient. Okay, so in our problem here, f of x, our constant is a -9. Now, do not worry about the sign because we will be looking at both the positive and negative values of these factors. Okay, so all I'm interested is in the value. Okay, so here the factor of my constant is 9, and the factor of my leading coefficient here is 1. And the rational zero test says this, that you are going to divide the factors of the constant divided by the factors of the leading coefficient, but I'm going to look at both positive and negative values. So on your homework or now on your final exam, when they ask you to list the possible zeros using the rational zero test, you would do these. You would do the division of each one. Now again, the plus or minus, we don't have a symbol for that. We're going to do them separately. So you would do I would put them more in order: 1, -1, 3, -3, and 9, -9. Okay, so when I divide the 1 with all these values, I'm going to get, these are all possible zeros. Okay, now where does this help us? Well, this means that now I can just test 1, 2, 3, 4, 5, 6 that can possibly give me a zero, and I'm not just trying numbers at random, then maybe not never find a zero. And this could possibly give me a zero. So I'm going to start with the first one. I'm going to just start with 1. And to speed up my process, I'm going to use synthetic division to see if 1 is a zero of this polynomial. Okay, so to recall synthetic division, the number that we're using to divide is just the 1 here. And we're only going to use the coefficients inside our little house here. So the coefficients here are 1 for the cubed, 1 for the squared, a -9 for the single term, and my constant, -9. Now, please keep in mind, when you're using synthetic division, don't be fooled. The polynomial has to be in descending order, it has to be in our general format. And if it's missing any term, we put a 0 in it. Okay, so in this one, we have all our terms. We have a 3, 2, 1 constant, and they're in order. So here they are. So now let's start. Synthetic division, the first thing I'm going to do is I'm going to bring down that 1. And then I'm going to multiply the 1 to the 1. So 1 times 1 is 1. And then I'm going to add 1 plus 1 is 2. Then I do it again. 1 times 2 is going to be 2. And then I'm going to add the -9 with a 2, which is going to give me the -7. I'm going to do it again. 1 times a -7 is a -7. And -9 plus -7 is -16. So what this tells me, since this is my remainder, the last value here is called our remainder. Since we have a remainder, then that means that 1 is not a zero of this polynomial. And we want a 0. If the factor that we're using was a 0, or gave us a 0 for the remainder, that means it's a 0 for the polynomial. So let's go ahead and try it again. So again, x equals 1 is not a 0. So let's try it again. And now let's use -1. So again, I'm going to bring down my 1, multiply by the -1. So -1 times 1 is a -1. 1 minus 1 is 0. Let's multiply the -1 times 0. -1 times 0 is 0. So -9 plus 0 is -9. Now I'm going to multiply the -1 times the -9. That gives me a +9. And -9 plus 9 is 0. This makes us really happy because now if you see here, this last addition gave us a 0. So what that means, since the remainder is 0, that is telling us that x equals -1 is a 0, right? Big happy face. So now that we have 1 0, we would be able to find the remaining zeros. And what I'm going to do is I'm going to use the quotient. This is the result that I have from my division, which is the quotient, and I can convert it back to an equation. And if you remember, when you're doing division, you lose a degree. So we had started with a cubic function, but with us the division, this first term here, that means now that I have a quadratic, so I have a square. So this one refers to the x squared. I don't have a single x term, but I have a constant, the -9. Now you can see that it would be easy to find the remaining two zeros. So to find the remaining two zeros, I said x squared minus 9 equals to 0. So I'm going to add 9 on both sides, take the square root of both sides, and simplify. And I see that x is equal to plus or minus 3. Now you heard me say that I had two zeros. Well, why did I say that? Well, since I had a cubic function, I know that I could have at most 3 zeros, and that's what I do have on this one. I had my first zero, which was x equals -1, and I have my other two zeros, where x is equal to a -3 and x is equal to a +3. So now I can graph. These are my zeros, and I can graph the polynomial. So the first thing that I would do is I would plot where my zeros are. I can use my behavior to find out more about the graph. So again, we have a odd function. Since the highest exponent is a 3, that means that the degree of this polynomial, since 3 is an odd number, then this polynomial is an odd function. Now, my leading coefficient, since it's a positive value, then that means that the graph is going to rise on the right and fall on the left. Okay? Now, it would be good to use some additional points just to see what's happening with a graph between our dots. So the best points that I would use is the points that lie between my green dots to get a better idea of the graph. So one of the points that I'm going to use is a -2, which falls between my first two green dots, and I'm going to use a +2, which lies on my other half, right? And then I use the -1 just to be a little bit more accurate. So here, when I picked x equals -2, I saw that my y value was a 5. And when I picked x equals 2, I saw that my y value was a -6. And then when x was 1, I saw that my y value was a -16. So I can now plot these points. And here they are. So the next thing I need to do is I try to do a smooth curve, right? Since I'm doing this graph on the computer, it's all wavy and crooked. But if I were to use the graphing tools from that you use, it would be a nice curve. But this is to get us an idea of what the graph looks like, again, for those multiple choice questions. All right, so let's go ahead and look at another example. This problem says, use the given zero to find all the zeros of the function. So on this particular one, we have a Q function, and we possibly could have at most 3 zeros. So they gave us one of those zeros. They say that 0 is equal to a 4 plus 2y. Oh, but this 4 plus 2y is a complex number. Now, just so you can see, we can still use synthetic division with complex numbers, and that's what this whole example is about. That even though I have a complex number, I can use synthetic division. Now, just to review, what is a complex number? A complex number is a number that is made out of a real part and imaginary part. So on this one, my complex number, I have a real part of 4, and I have an imaginary part of 2y. Now, what does it mean to be imaginary? Well, this came from when we have a square root of -1. Since originally we knew that the square root of -1 was an error, it's undefined, but now we know that the square root of -1 can be considered an imaginary number. So this is the value of I. Okay, so let's go ahead and practice synthetic division with complex numbers. Again, I have a Q function. Is it in order? 3, 2, 1, constant. Yes. Do I have a placement value for all of them? Yes. So I have a value for the 3, for the 2, for the 1, and for the constant. So let's go ahead and put our coefficients only. We don't put any other variables. We just put the numbers. So we have a 1, -12, +52, -80. Okay. Again, we bring down our 1, and then we're going to multiply 4 plus 2i with a 1. We get 4 plus 2i. When we add these two numbers, we're just adding the real parts. -12 plus 4 is a -8. We didn't have an imaginary part, so 0 plus 2i is just a 2i. Let's go ahead and do this again. I'm going to multiply 4 plus 2i times my negative 8 plus 2i. This would be just a FOIL, okay? And we have this negative 32 plus 8i minus 16i plus 4i squared. We can combine our like terms, and we know that I squared refers to a negative 1 value. So we have this. Oh, and I didn't put it. So we have a 4 times a negative 1 is a negative 4, and 8i minus 16i is a negative 8i. And this is where I'm at now. I have negative 32 minus 8i minus 4. I can combine more like terms. I have my two real parts, the negative 32 and the negative 4, which is going to give me a negative 36. So now I can add. Again, the 52 is the real part that adds with the real, the negative 36, which gives me 16. I don't have an imaginary part, so 0 minus 8i is just a minus 8i. I'm going to do this again. I'm going to multiply 4 plus 2i times 16 minus 8i, and I get this quadratic, but again, I can simplify it. 2, it's going to give me 64 minus 16i squared. Okay, I'm going to add the real with the real, the negative 80 with a 64. Um, but before that, sorry, let me simplify it. Let me simplify the I squared. Again, I squared is a negative 1. So a negative 1 times a negative 16 is a positive 16. So I'm going to add 64 with a 16, which is right here, 64 plus a 16, which is going to give me 80. And negative 80 plus 80, is 0. And again, this has made us very happy because our remainder was a 0. So that means that and we knew this, right? The 4 plus 2y gave us a 0. But the reason why we did this was to simplify our polynomial, make the polynomial from a cubic to a quadratic. Now, why do we want to always work with a quadratic? Well, for the cubic function, there's not a formula to find the zeros, but for a quadratic function, we have formulas to find zeros, right? We have factoring techniques and we have our quadratic formula. So on this particular problem, it gave us this. Our quotient is x squared plus minus a plus 2ix plus 16 minus 8i. But this is a little difficult to work with. So what we can do is let's go ahead and divide again. Let's go ahead and use our synthetic division. So if we can simplify this even further, and maybe we can get rid of our imaginary, or sorry, our imaginary numbers or our complex numbers to make this problem more feasible. All right, so let's do synthetic division again. And then my value that I'm dividing by is the 4 minus 2i. Now before, let me go back. I used 4 plus 2i, but why did I change the sign? Why did I do 4 minus 2i? Well, if you recall, when you're taking the square root, I said that the imaginary number came from the square root of negative 1. But when you take the square root, remember you have always two values, a plus, positive, and negative. So I'm just using the other half, okay? So here, I'm going to bring down my 1, multiply. We get 4 minus 2i. The way we add complex numbers is always real with real, imaginary with imaginary. So minus a plus 4 is a minus 4. The plus 2i minus 2i is 0. We just have the negative 4. We just have a real part. So now let's do it again. Multiply 4 minus 2i times the negative 4. And we have negative 16 plus 8i. This is easy to see that when we add 16 minus 8i minus 16 plus 8i, we get 0. Now, what are we left with? We started with a quadratic. So now we have just a linear, right? X, this one value refers to my x. The negative 4 refers to my constant. So now it would be easy to solve for the 0. So if x is equal to 4, this will give us a 0. So now we have all the zeros. The zeros are x equals 0, 4 plus 2i, and the 4 minus 2i. Okay. All right. Now let's look at another example. Maybe this might be our last one. This is considering a rational function. So what is a rational function? Is a function that is a fraction, right? So as before, when we were looking at functions, our denominator should never be equal to 0 because then we have an undefined. Okay. So on this problem, can we state the domain? Well, will the denominator ever give us 0? So if we don't see it, we can set this equal to 0 and see if x gives us a 0. So let's do that first. So to do our solution, here we go. Um, if you don't see it, we set x plus 3 equal to 0. And we do this, we solve, we see that x is equal to a negative 3. So if we were to use negative 3 here, you would see that it would give us a 0 in that denominator. So that's a restriction. So again, in words, what does this mean? That means that we cannot use negative 3. We can use all the real numbers except for only one, negative 3. So what would be our answer? Our answer would be this last one, right? It would be, there we go, this last one. All right, so let's answer B. It says, identify all intercepts. So again, if I want to find the x-intercept, I set y equal to 0. If I want to find the y-intercept, I set x equal to 0. So let's do the x-intercept first. So let's set y equal to 0 and solve for x. So here, f of x is replacing the variable y, so we'll set it equal to 0. So we have 0 is equal to 1 over x plus 3. I'm going to multiply both sides by x plus 1, and I have 0 times x plus 3. I know that's going to give me 0, and x plus 3 divided by x plus 3 is 1, and 1 times 1 is 1. But here we end up with 0 is equal to 1. Do we have a true statement? Well, the answer is no. This is a false statement. So since we have a false statement, that means that this function has no x-intercepts. And again, we would answer it by D and E, does not exist. There aren't any. Okay? Let's go ahead and find our y-intercept. So again, to find our y-intercept, we're going to set x equal to 0. So everywhere we see x, we're going to plug in 0. And when we do this, we have 1 over 0 plus 3. And 0 plus 3 is just 3, so we have 1/3. So our y-intercept, when x equals 0, y is equal to the 1/3. Okay? Now, C, it says find any vertical and horizontal asymptotes of the equation. Okay? So for the vertical asymptotes, those are easy. If we had a restriction in our domain, or there was an x value that we could not use, well, guess what? That is our vertical asymptote. Okay, so and for a horizontal asymptote, there's several conditions that we have to meet to find that, but we'll do that. Let's do first our vertical asymptote. So again, to find your vertical asymptote, you set your denominator equal to 0, which we had already done to find out if it had um, um, an intercept, and we see that our vertical asymptote we couldn't use, or the value that we could use was x equals negative 3. So x equals negative 3 is our vertical asymptote. Okay. Now, so it's this imaginary vertical line. We represent that in a graph as a dashed line. Here on the graph, they look like bubbles, but it's supposed to be dashed. Okay. And for our horizontal asymptote, I got 3 more minutes. What we have to do is we have to have these cases. Okay. If the degree of the numerator is smaller than the degree of the denominator, we'll always have a horizontal asymptote at y equals 0. If the degree of our denominator is equal to the degree of our numerator, then we have a ratio for our asymptote. And if the degree of the numerator is bigger than the degree of the denominator, we have no horizontal asymptote, but that means that we'll have a slant asymptote. So let's look at our problem really quick. And if we see here, if I were to write the numerator as x to the 0 power, anything to the 0 power is 1. But you would see that 0 is smaller than the degree of the denominator, which is a 1. We don't put it here, but here, the degree of the numerator is smaller than the degree of the denominator. So hence, we have a horizontal asymptote at y equals 0. Okay. Now that we have our horizontal asymptote, we have our vertical asymptote, we have our y-intercept, we know that it doesn't have an x-intercept. We can plot additional points to get a better read off this graph. Again, I'm just going to pick negative 2 and 2. When I plug these in together, again, I get these points. I plug them in my graph. I do apologize that I'm going fairly quickly, But again, you will be able to download this presentation after we leave, okay? So again, using a graphing tool, connecting the dots gives us this really, really nice graph, okay? All right, so again, thank you for joining me to our last session. I hope you guys enjoyed them. Do apologize. We had some technical difficulties. But again, I'll go ahead and pass it on to our presenters.
Thank you, Mr. Carrizales, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on the YouTube playlist. Today's session will also be available on that playlist later on today. Also linked is a short survey to help us improve our TVE sessions. Please take time to fill out the survey. It does help us. Thank you all for coming in today. We all hope that you will have a lovely weekend. If you have any questions, feel free to use the chat box or the mic to ask Mr. Carrizales any questions. It is a reminder that this will be the last session for Happy Math Hour for this semester. We will have a student success topic today at 1, which will be covered by Tejano Mercado, the food pantry, with Campus Life. And good luck to everybody on your finals. And thank you for joining us today.
I'm gonna upload the file in case you wanna download it. You can download it by clicking the arrow. Give me a second. For the presentation. No, it's okay. My fault. So you should be able to click the file. There's a box with an arrow pointing down. If you click on that, the file will be downloaded to your computer. And we wish you the best.